Good morning, everybody. I'm Sebastien from Kalray, and in this keynote, I will talk about the usage of programmable DPUs to unlock the full potential of NVMe-oF Fabric and software-defined storage. So, during the last 2 decades, we have seen the data center world moving to a software-defined everything paradigm. Up to now, this has been taken care of mostly by hypervisors running on the x86. In parallel to that, a new communication protocol has been specified to fully exploit the levels of parallelism and performances of all-flash storage. So basically, the first version is NVMe, and its fabric version, NVMe-oF Fabric. We believe that to fully unlock the benefits of NVMe-oF while keeping the software-defined paradigm, a new processor kind is needed, the data processing unit, or DPU. So let's start by a quick introduction of myself. So as I said, I'm Sebastien Leduc. I'm currently Software Engineering Director at Kalray. I started my career at STMicroelectronics in 1998, and I spent almost 20 years in the semiconductor industry, working on different complex system on chips, well, mostly on software on those complex system on chips. And I joined Kalray 2.5 years ago, and I am now the Kalray Software Engineering Director. So here is the agenda of this keynote. So I will start by a quick presentation of Kalray. Then I will share some background information about NVMe and NVMe-oF Fabric. Then I will try to define what makes up a DPU, so what are the key characteristics of a DPU. And then I will switch to a use case section where I will present 3 different use cases, storage use cases, where DPUs bring a lot of added value. And after that, we will reach the conclusion of this keynote. So let's start with a quick presentation of Kalray. So Kalray is a French public company, is backed up by industrial investors as well as by European governments. Basically, Kalray offers a new type of processor which targets the booming market of intelligent systems. This new type of processor has a many-core architecture, and it's called MPPA. And we are currently at the 3rd generation of our MPPA processor. In terms of markets, we target 2 main markets. So the first one is next generation embedded systems, and the second one is next generation data center infrastructure. So obviously in this talk, I will focus on next generation data center topic. Okay, I will now go back to some background information about NVMe and NVMe-oF Fabric. So if we do a bit of history, so the first NVM Express specification was released in 2011, so 10 years ago. It is a logical device interface specification that has been specified from the ground up to capitalize on the low latency and internal parallelism of solid-state storage devices. And the first specification, so NVMe, was addressing only storage devices attached via the PCIe bus. Then in 2016, we got the first NVMe-oF Fabrics specification released. So basically, NVMe-oF Fabrics extends the NVMe command set to enable using it over a network. the first specification, the first version of the specification had support for different types of fabrics, so fiber channel, Rocky, iWarp, and InfiniBand. And basically, with NVMe-oF fabrics, it enables the benefits of the NVMe technology to be used, to be realized at a much larger scale than the PCIe allows. And then in 2018, the NVMe TCP specification was released. So basically, it's the version that allows to use NVMe-oF fabrics over the TCP/IP network. And this is quite key, as it enables to use NVMe-oF fabric using existing network infrastructure. So as you can see, NVMe has been around since 2011, so for 10 years. NVMe-oF fabrics has been around for 5 years. So you may wonder why now? I mean, what makes it different? Why we think it will now really start to be adopted. So first, NVMe is already being adopted. So we see a dramatic change with a huge growth in SSD adoption in the storage market. And we see that SSDs are improving at a much faster rate than CPUs in terms of performance. So this leads to inefficient processing and also to wasted storage. We can today see that the two standard ways of dealing with storage are becoming problematic. So the first one is software-defined storage based on virtualization techniques. So we see that the virtualization with the hypervisor on the x86 is now becoming a bottleneck, and it can no longer sustain the speed that NVMe-oF fabric enables. And the second standard approach, basically legacy x86-based flash array solutions, we see that those solutions have a problem of price point, and we believe that there is room for disruptive solutions that will basically solve those two issues. So I have included in this slide a quote from Omdia analyst, which is planning that NVMe-oF fabric will ramp up aggressively for the next couple of years. Okay, let's now try to define what makes a DPU and why it is really a different kind of processor. So what is a DPU? So in the data center, a DPU is a new class of programmable processor, which is specialized in running data center infrastructure services. Basically, it's aiming at becoming the third socket in data centers alongside the CPU and GPU. And basically, DPUs are purpose-built for accelerating software-defined data center infrastructure services. So I have named a few, given a few examples. So for software-defined networking, just as examples, I've taken virtual switching, NFV or NAT. For security, the DPU can accelerate firewall, encryption, IPsec, and of course, for software-defined storage, it can accelerate NVMe-oF fabric. It can accelerate compression, deduplication, encryption, or even erasure coding or RAID, this kind of data services. So in terms of key features, so what are the key features that make a DPU? So, well, the first one is that a DPU must be fully programmable. I mean, the three planes must be programmable. So management plane, control plane, and the data plane, which of course is the most tricky one, because we are talking about high-speed interfaces and having a programmable data plane as at those speeds is really a challenge. Then a DPU must have a high-performance PCIe interface because it's aiming at becoming the third socket in the server. It has to have a PCIe interface, and this PCIe interface must have SRIOV support because virtualization is ubiquitous in data centers. Of course, it has to have high-performance network interfaces with features that will allow to use and process packets coming from those high-performance network interfaces. So, for example, packet parsing, packet matching and dispatching, RDMA support, of course, some TCP offload functions like RSS, large receive offload or checksum offloads. Then the DPU must also feature some tightly coupled inline accelerators because there are key functions that are part of data center infrastructure services that need to be accelerated by dedicated accelerators in order to be able to sustain the rates, the line rates. So examples are crypto accelerators. So this is to accelerate IPsec, for example, or TLS. Other types of tightly coupled inline accelerators can be compression and erasure coding acceleration for storage. And of course, as any programmable processor, a DPU must have some security features. So just as examples, it must have a root of trust, a secure boot, possibility to upgrade its firmware securely, and a vault IP to securely store cryptographic keys. Okay, so all those features are what really make a DPU different from a normal CPU. Let's now look at the current DPU landscape. So on this slide, you can see a few companies that have DPU products today, or products that are marketed as DPUs today. So out of those, you can see 3 big semiconductor companies, so NVIDIA, Broadcom, and Marvell. And you can also see 2 smaller companies, so Fungible and Kalray, of course. So let's have a look a little bit more in details to the details of the products offered by those companies. So the first one is NVIDIA. So NVIDIA's current DPU product is NVIDIA Bluefield 2, which is formerly a Mellanox product, which got acquired by NVIDIA. So Bluefield 2 is essentially ARM octa-core CPU plus Connect X6 network interface card in the same die. So basically, they took the two and just made a single die version to get the Bluefield 2. So it features PCIe Gen 4 16-lane interface. It also has 2 100 gig Ethernet interfaces. So as you can see, it seems to fit pretty well the definitions of DPUs that we gave just before. Then we have the Broadcom Stingray, which is fairly similar. Again, it's essentially ARM octa-core CPU and a Broadcom Net Extreme NIC in the same die. It is only PCIe Gen 3, and it only has 1 100 gig Ethernet interface. The next one is Marvell. So Marvell has the Liquid IO 3 DPU, which is formerly a Cavium product that was acquired. Cavium was acquired by Marvell. So the Marvell Liquid IO has a bigger, well, it's still based on an ARM multi-core CPU. It has more core than the 2 previous DPUs we talked about. So it has 24 cores, which is quite big. They have a PCIe Gen 4 by 16 interface and two 100 gig Ethernet interfaces. So looking at the specification and the way they market the liquid I/O, it seems that it's more targeted to software-defined networking than it is to software-defined storage. Okay, let's now switch to the two, let's say, challengers, so Fungible and Kalray. So Fungible has the F1 DPU. So the F1 DPU is based on a mini-core architecture, so quite similar to Kalray. It has 52 Mix64 CPUs. It features 4 PCIe Gen 4 16-lane interfaces and 8 100 gig Ethernet interfaces. Okay, and now I will go a little bit more in the details of the Kalray MPPA Coolidge on the next slide. So here is a quick summary of the main features of Kalray MPPA3 Coolidge. So as I said, the Kalray MPPA3 Coolidge is a many-core architecture. So it features 80 CPU cores, which are VLIW cores. Those 80 cores are gathered into 5 clusters, and they all run at 1 gigahertz. One important point is that each cluster has some local memory, quite a big amount of local memory, which is a key feature that enables our product to be so efficient. In terms of power efficiency, it has a 20-watt typical power consumption for data center applications. In terms of high-performance interfaces, it has 2 100 gigabit Ethernet interfaces and 1 PCIe Gen 4 16-lane interface. It's fully programmable, so this is one key characteristic when the DPU is based on a many-core architecture, is that all 3 planes are fully programmable. So we have basically, in our case, the control and management planes that will run on one cluster, one of the 5 clusters. So basically, in that case, the cluster is seen as a 16-core SMP CPU running Linux, which makes it easy to port any kind of existing legacy software. And we have the data plane that will run on the 4 remaining clusters. So in that case, it makes 64 cores, and for storage applications, basically the data plane runs SPDK. So we have a software solution that is based on SPDK ported to our data plane, which makes our data plane for storage fully programmable. Okay, the next key point is tightly coupled accelerators. So in the MPPA, we have 10 crypto accelerators, as well as some erasure coding acceleration and some advanced programmable DMAs. Of course, we have all the required features for security. So be it root of trust, secure boot, or a secure vault to store cryptographic keys. In the second part of my keynote, I will go through 3 use cases where using DPUs makes a big difference. So the first use case is basically the main use case for which NVMe-oF Fabric was invented, namely disaggregating local SSDs. So the idea is pretty simple. On the left, you have servers with direct attach SSDs, and the idea is to disaggregate the SSDs by putting them in an NVMe-oF Fabric all-flash array. And so basically, the local SSDs now become a shared pool of storage that is visible to all servers thanks to the NVMe-oF Fabric protocol. So this has a number of advantages. So the first one is that servers can now be composed on the fly with just the storage requested, whereas on the left, you basically had hard-coded configuration with a number of direct attach SSD in each server. So this, of course, results in better resource utilization and then, of course, has a decrease in costs. The second advantage is that thanks to this new architecture, since the disaggregated SSDs are visible as a shared pool of storage, it's now much easier to move workloads from one server to another one, because you just have to reattach to their volumes after moving them. And another big advantage of this approach is that you can now scale storage and compute independently, again, allowing to reduce the costs. So, of course, shared storage is not new, but thanks to NVMe-oF Fabric, it's the first time we can have both shared storage with performance close to that of direct attach SSDs. So there are a number of ways to implement NVMe-oF Fabric all-flash arrays, and I will try to compare those different ways of doing along two KPIs. So the first KPI is on the x-axis, IOPS per dollar. So basically, this is a very good indication of the TCO optimization you can get from switching to one solution. And the second KPI that is of interest is IOPS per watt, because power consumption is becoming really an issue in data centers. So we think this KPI will become more and more important in the future. So let's look at the first solution that I call storage vendor solution. So basically, all major storage vendors have some NVMe-oF all-flash array in their catalog today. Those solutions are based on x86 platforms. They are very feature-rich, but since they use some software stack that has not been designed for NVMe parallelism, they are not able to fully exploit the performances that is available thanks to NVMe disks. And the result is that the performances are not as good as what we would like. They are also pretty costly. This is why, in terms of IOPS per dollar, they are not very good. Then another category, still based on the x86 platform, is basically what I call x86-based all-flash arrays, on which you put a software stack like SPDK that has been designed from the ground up to exploit the parallelism of NVMe disks. In this case, you end up with a solution that is an order of magnitude better than the one of storage vendors. But in terms of feature, it's very difficult to put all the storage features while still keeping the performances. The more you add data services, the more the performances will collapse, basically, because the x86 is a general purpose processor, and you don't have the hardware dedicated tightly coupled accelerators that DPUs have that allow them to cope with the additional data services. And of course, the third solution is to build an NVMe-oF all-flash array using DPU cards instead of using a x86. So basically, in this case, since the DPU has hardware accelerators to accelerate data services, it's able to cope with running more data services without decreasing the overall performances. And we see that today a DPU is the best solution when you look at IOPS per dollar, so in terms of cost, versus the two others, or even better in terms of IOPS per watt, because DPUs have a much lower power consumption than x86-based platforms. So in terms of data services, let's go a little bit more into the details of all the data services that are needed to make a storage node, let's say an NVMe-oF storage node. So there are some basic services like TCP termination for NVMe-oF TCP, which takes quite a lot of software processing. Logical volumes, scene provisioning, and snapshots are, of course, basic services that are needed on any storage appliance. And then we have some other data services that are much more processing hungry, like data reduction, data availability algorithms, or data security. So here, the DPU is able to cope with all those data processing services at line rate much better than the x86 because it features some dedicated hardware accelerators like compression acceleration, erasure coding acceleration, or crypto acceleration. And thanks to those accelerators, the DPU is really able to sustain the required performances. So this is why we believe the best solution to implement an NVMe-off Fabric all-flash array is by relying on DPU cards. Let's now switch to use case number 2, which I call storage adapter for SSD disaggregation. Basically, use case number 2 starts from where we left in use case number 1. So on the left, we have our situation where we have disaggregated SSDs by using an NVMe-off Fabric all-flash array. The all-flash array usage brought quite some advantages, but there are still some issues. The first problem is that you need an operating system on the server that has NVMe-off Fabric support, of course, which is not the case of all operating systems supported today. Another issue is that it's not possible today to boot from SSDs exposed via NVMe-off Fabric, which means that you will need another medium to boot from, be it another shared storage like iSCSI or local SSDs. Just to boot. There is still room some improvement. So this is where the storage adapter comes into action. So the idea is to put a DPU card with a storage adapter software on it in each of the server. And I will explain a little bit more what this storage adapter will do. So the idea is that the DPU in the storage adapter will present itself as local NVMe disks to the host server, and it will be basically the storage adapter that will manage the NVMe to NVMe-off Fabric translation. So that's why we call it an adapter. The advantages of this solution is that you no longer have any requirement on the operating system because basically now the server only sees NVMe, and NVMe is supported by all current operating systems. It also means that you can really exploit this mechanism to do bare metal server virtualization, basically. The second good property of using a storage adapter is that now that the server only sees NVMe, it can boot from this NVMe, and it will be the storage adapter that will do the translation to NVMe-off Fabric. So at the end, you are now able to boot from NVMe-off Fabric disks. And all that is fully transparent to the bare metal server. If we now focus on the NVMe to NVMe-off Fabric translation, the translation can be configured by some orchestration software that will interact directly with the DPU through the network, so either inbound or out of band. So you don't need any orchestration software on the bare metal server, and it also means that you can move workloads from one bare metal server to another one, which is pretty nice. So really, as you can see, thanks to this storage adapter in servers, we enable bare metal storage virtualizations by using DPUs. In terms of data services, this storage adapter is bringing a lot of opportunity for system optimizations. In terms of basic services, the DPU will have to handle all the bare metal storage virtualization. So basically, it will have to provide some APIs to the orchestration software so that the storage virtualization can be configured. The storage adapter, so the DPU, must also, of course, implement the NVMe emulation in order to be able to present itself as a NVMe local drive. It also has to support NVMe initiator functionality in order to translate from NVMe to NVMe-oF Fabric, which by the way, implies that the DPU is running a networking stack. And of course, there are some QoS considerations because you may want to have QoS settings different and configured by the orchestration software. So as you can see, thanks to a DPU, we enable bare metal storage virtualization and it's fully software defined. Other opportunities for running data services on the storage adapter. So we can, for example, have data reduction algorithms running on initiator side, which has some benefits because it results in lower network bandwidths. And in terms of data availability, now that we have a DPU on initiator side, it allows us to have much better data availability schemes like distributed erasure coding, which enable better reliability while improving storage efficiency. And in this case, again, the mapping of volumes is fully software defined by software running in the DPU and configured by the orchestration software. Similarly, you can have data security services that will run in the DPU. So you can, for example, have encryption in motion that is transparent to the host server that still sees only NVMe drives without knowing that behind the scene there is some NVMe-oF Fabric translation going on and that this NVMe-oF Fabric is encrypted, connection is encrypted. Again, the security configuration in that case is fully software defined and can be controlled by orchestration software. So as you can see, using a storage adapter in each of the server brings a lot of new possibilities, and especially for bare metal storage virtualization. Let's now switch to the third use case I want to talk about today. So the third use case is called storage adapter for hyper-converged infrastructure. Similar to use case number 2, but still a bit different. On the left, if you take a standard hyper-converged infrastructure, you have identical servers, each with both some compute and some storage, so some local disk in each server. The idea is to put some storage adapter in each of those hyper-converged servers and use those storage adapters to provide a global data store repository to the full HCI cluster. The idea again is that the storage adapters will connect to each other, and in order to provide a distributed pool of SSDs that become visible to all the storage cluster. So I will go a little bit more into the details in the next slide. In this use case, the idea is that the DPU takes ownership of the local drives in the HCI server. This is using the PCIe peer-to-peer technology. You can have the DPU that will read and write to the local SSDs. So it can really take ownership of the local drives that are no longer under the control of the host server. Then the DPU Similar to use case number 2, presents itself as local NVMe disk to the host server, and the DPUs that are in each of the servers kind of connect to each other and provide a global data store made of all the distributed local drives of the cluster. And this becomes a global data store exposed to the host servers. So in this case, each DPU will act as both a storage target and a storage initiator. And storage is fully virtualized without needing an hypervisor. And of course, this virtualization is fully software defined by software running in the DPU that is configured again by orchestration software. You also have the opportunity to use NVMe-oF Fabric all-flash array in addition to using storage adapters, which enables to increase the size of the global repository just by adding NVMe-oF Fabric storage nodes in your infrastructure. And this is fully transparent to the servers. They just see additional storage that can be used. And in terms of data services, so this is quite similar to use case number 2. We end up with the DPU that has to support bare metal storage virtualization software. Again, it needs to implement NVMe emulation to present itself as local disk to the servers. It has to implement NVMe-oF target and initiator in this case, because the server, when writing to a volume, may write either to a local drive behind the scene or to a remote drive. So similarly to use case number 2, in the DPU must run some networking stack and some QoS features. And again, all that is fully software defined with software running on the DPU and orchestration software that can configure it. Similarly to use case number 2, we can do data reduction and data availability algorithms or data services that are again fully software defined. And you can now, for example, have distributed erasure coding inside your HCI infrastructure without decreasing the performances, because as you may know, in HCI solutions, HCI software solutions, erasure coding is usually not enabled by default because the performances decrease quite a lot when you enable it. Thanks to a storage adapter, you can now offload completely this distributed erasure coding, and you can now enable it all the time. Another good property of using storage adapters is that it enables to use HCI infrastructure for bare metal workloads or bare metal use cases, whereas while still keeping the flexibility of storage virtualization. So this is really something new, and that can be only achieved thanks to a storage adapter based on a DPU. Okay, let's now switch to the conclusion. The NVMe SSDs and NVMe-oF Fabric will disrupt the storage markets. That's what we are already seeing on the market today. I mean, the NVMe SSDs are adopted very quickly, and NVMe-oF Fabric is following. Today, we really see that software-defined storage based on virtualization will become a bottleneck to leverage the full potential of NVMe-oF Fabric. And we believe that DPUs are the solution, and this is what will allow to unlock the full potential of NVMe-oF Fabric while keeping the flexibility of software-defined storage. Thanks a lot for your attention. Goodbye.